Okay, it's time to start. Welcome to CALOP Eat and Learn seminar. Welcome to everybody. Today we have a very valuable speaker. His name is Suho Shin. Suho Shin. And let me briefly explain his background. He graduated from KAIS in undergraduate mathematical science major and master in electrical engineering major. And then he went to United States and University of Maryland, College Park, PhD program in computer science. He is a PhD candidate. He's about to graduate soon, right? So today's the topic is algorithmic game theory introduction and recent progresses. So according to his resume, his main research area is in mechanism design and market design. So there are some connection between economics and optimization. So he has very good publications. So I'm very happy to invite him. Please welcome him.
Hi everyone, I'm Suho Shin. Thanks a lot for introduction and invitation for this very wonderful seminar. I've been mainly studying algorithmic game theory, which is an intersection about computer science, economics, and also operations research and industrial engineering. It's very interdisciplinary area, and there are a lot of researchers on all of these communities working on these problems. There's not a very famous topic 2 decades ago, but it has been very emerging topics especially in the United States because of a lot of modern online platforms with applications having in these topics for example ad auctions, a lot of data markets, some matching problems between schools and students or so. Today, the title of the talk is Algorithmic Game Theory, Introduction and Recent Progresses. I will not talk about technical, very detailed technical results or techniques to actually solve specific problems, but rather focus on what is this general topic is about, and what are some minor problems studied in this literature, and also what are some recent trendy topics in this community. The outline of the talk will be, I'll be first give some distinction between basic game theory problems and what the objective of the algorithmic game theory is trying to do, and also a little bit of community information, for example conferences, some communities, some logistics information, so that you can have a little bit more accessibility to this community. And also I will introduce some of the representative problems in this literature, and also some of my recent works in this. Feel free to ask any question. I think all of you would be familiar with the algorithm design. So for example, suppose that you need to travel from here in Pohang to Seoul, for example. There are two routes that you can take, and the time that is required to travel in each of the routes, for example. Then what you're gonna do is the typical algorithm design, to solve a shortest path problem, for example, given some nodes of the graphs. You can solve this using some standard algorithms. But suppose that there are two drivers. If there are more drivers in a single road, it is expected that there are increasing number of routing times to actually go through that road, right? So in this specific example, okay, they can actually coordinate so that I will take this road, or so that you can take another road to minimize our overall welfare for both of us. But what happens if there are like a lot of like drivers trying to do like solve some similar problems? So this is actually what is a game theory about. So game theory is to study the systems when there are like multiple strategic agents who try to solve like their own objective function and their own optimization problems. So the like one very different thing about like just the standard optimization is that each agent has its own objective function, but its objective function not only depends on that agent's like action, but also on some other agent's actions as well. So what we are like asking in this scenario is that like what will be the stable outcome, or for example, like what is the expected outcome of these systems involving like multiple strategic agents, and whether like those outcomes will be efficient or not. Okay. So like formally, there are in game theory problems there are n game players. We often call them as an agent, and each agent has an action space AI. And there's a payoff function, which is an objective function for each of the agent, which is a mapping from all of the agent's actions to some real value. Okay. And okay, so like suppose that this action space is just a like finite space for now, and then agent can also randomize over the actions. For example, like with probability 0.5, I take this action, otherwise I take another action. Okay. So that is actually called as a like mixed strategy in game theory. So like this is a very like famous example in game theory, which I believe like many of you have heard about, which is called as a prisoner's dilemma. So as you see, like there are payoff functions for each agent, each player A and B. So the right part is the payoff function for the player B and the player A for the left side, corresponding. Okay. So like there are several like a lot of solution concepts for game theory problems, because like everyone there's no single solution, because like everyone is trying to like solve their own optimization problems, which depends on everyone else's like actions. But one of the most like typical solution concept here is what is called as a Nash equilibrium. It is about quite a stable outcome where when they commit to this strategy profile, then there is no incentive for anyone else to deviate from that strategy profile. Okay. So like mathematically speaking, UI, SI, comma S minus I. Here, S minus I is an abbreviation for everyone else's action profiles except the player I. It should be at least better than UI SI prime, S minus I, or any other possibly mixed strategy SI prime. And I think it will be informative to define a little bit of stronger notion of the equilibrium, which is called as a dominant strategy equilibrium. So in here, you're given a strategy profile and no one else tries to deviate, has an incentive to deviate from that. But in the dominant strategy equilibrium, which is actually like the stronger notion of the equilibrium, regardless of other strategy profiles, S minus I, the agent should be better off playing the strategy profile SI. Okay. So there are a lot of like extensions of these notions of Nash equilibrium, which is developed to better capture the real world scenario and to better make the problem a little bit more tractable, to better capture a little bit more broader set of applications. Okay. So this was about game theory. So this is about like analyzing Nash equilibrium given some games. So like typical researchers in these areas to, okay, I have this game, I analyze some equilibriums, here are the results, this is efficient or so. But there's another branch of the like game theory, which is called as a mechanism design. So this is actually often called as a reverse game theory. So this is rather about designing a game rather than analyzing a game. So this is about, for example, Okay, I want, for example, I have an item and I want to sell this item, but I want to sell this item to strategic buyers. And what I want to do here is that, like, okay, I know that like buyers are strategic. I know, and then knowing that, I want the equilibrium outcome of my game to be somehow like stable and desirable. Okay, so the mechanics design is generally about designing a game so that the equilibrium outcome of the game is desirable from my perspective. So there are a lot of like real world applications based on these mechanics design problems. One of the most seminal problems is perhaps the auction theory, which also got 2 Nobel Prizes in economics, which is about like, okay, how to sell items to buyers. There was also another variant of that, like concerning multiple sellers and multiple buyers, which is often called as double auctions. And also there is one very big branch, which is called as a principal agent problems, which is also a version of the mechanics design problems, but a little bit different applications than auctions. So in the principal agent problems, for example, if you want to hire a secretary in your department, for example, how you're gonna decide the contract between 2 mutual parties, and like how you're gonna like design a screening rule to hire someone who is smart and who is like dedicated and committed to the department. And for example, if you're gonna run, so for example, there is a lot of like contest, like data science and algorithm contest in this. In the past few decades. So for example, in Kaggle, how are you gonna design the rule of the contest so that you maximally incentivize the participants to exert their like maximal efforts? Okay? So this was about principal agent problems. And there's another branch which also got Nobel Prize in economics, which is called as a matching theory. So this is quite like very a graph theoretic like problem. For example, suppose that there are like hospitals and patients. They have some preferences for each of them, and then how we're gonna like match all of them so that they have no incentive to lie about their actual preference, or for example, the outcome is quite efficient in the sense that they don't like envy someone else's matched hospital or so. This has also like a lot of applications, for example, like students and schools matching problem, and also how we're gonna like match roommates in dormitories. Like especially this auction theory has a lot of like applications. For example, if you think about e-commerce like Coupon or Amazon, when you like search some keywords, there is always this like sponsored product. So this is actually like exactly defined by an auction. So whenever we type a keyword in this application, then the platform has millions of advertisers who actually bid on specific keywords in advance, and using that bids and using some like prediction algorithms, they estimate some expected revenue of like putting these items to the sponsored like position, for example. And then they run some auctions based on some predetermined auction format. It could be something like second price auction or first price auction. And then what these auctions actually do is that like it determines the allocation function and payment function. So allocation function is that who is gonna get the position number 1, position 2, something like that. And payment is gonna be you're getting this position, then you're gonna need to pay this amount of money. So this is what the auction is actually doing in this example. Like, so whenever you type, like you write some keywords in this platform, every time like there is like auction like going on for every instruction. And that is exactly the same for what is called as a display ad auction. So whenever you enter some websites, you may have watched some of the advertisements like shown in the next of the website. So that is exactly like running in a similar manner to the sponsored search auction. So the only difference is that there is no keywords here. So we're sort of like just like recommending the advertisements that the user is most likely like prefer, or it's gonna like have like higher probability to actually click the advertisement. Okay. So like the reason that we're using like Google's, Facebook, Instagram's, TikToks, and all these platforms for free is that like because they're like earning like tons of revenue from running these auctions, ad auctions. And also there is what is called as a spectrum auction. For example, like companies like KT, SKT, LG, they are actually like buying the spectrum license from the government. And in that process, the government's actually like throwing an auction. They bid in a simultaneous manner, and then the government, based on some predetermined auction format, they decide who are gonna win this spectrum frequency and how much they're gonna pay. Okay. And there are a lot of like applications for matching problems as well. As I said, like school students matching, hospital like patients matching. And also, like if you think about the electoral system, this is all about game theory as well. So you can probably strategically like select some other candidates that you don't prefer because like you sort of like think that maybe improve your outcome. Also contract, as I said, and also hiring some secretaries. And also there's a very like algorithmic question in this line of literature, which is called as a fair division problem, which is actually about like given some, so actually economics is all about given a very scarce set of resources, how we're gonna actually divide the resources efficiently and in a fair manner. So that is all about economics. So money is just a tool to make that interaction a little bit more smoother. So actually, this fair division problem is about like, okay, I have some roommates and we have to like pay some rents, and how we're gonna like divide our rents in a fair manner. So there is a lot of like literature on studying a fair an algorithm to fairly allocate some resources, so that the outcomes are sort of like efficient and fair, and nobody complains about that. And it has a lot of applications to like a lot of like real world like problems there. Okay. So I will talk a little bit more about some classic results from game theory. So as I said, game theory was all about like analyzing equilibrium. But okay, so there is a seminal result by Nash in 1934, proving that every simultaneous game with a finite number of players, finite action space, has at least one potentially mixed Nash equilibrium. Okay? There is also some seminal results from mechanism design literature showing that if you think about like selling multiple items, if you try to maximize the social welfare of the trade, there is what is called as a VCG mechanism that maximizes the social welfare for every sort of like valuation, combinatorial valuation functions for the buyers in a very like complex scenario, which is very like elegant results actually. Okay? But actually these results do not talk anything about how we're going to actually compute this mechanism, how we're going to actually compute the Nash equilibrium. So that is actually the limitation of the classic like results in economics and game theory. And also there are a lot of like actually in very pessimistic set of results in like classic game theory literature. For example, there's if you think about some voting problems where each of people here, Alice, Bob, and Carol, they have some like certain preferences on candidates A, B, C, and D, and then how we're gonna design the electoral roll so that the outcome is sort of like robust in the sense that they don't lie about their actual preferences. For example, there is an impossibility result stating that any non-trivial voting row is always manipulable, so that somebody can always like distort the outcome of the voting system here by like misreporting their actual preference. Okay. And also there's also some like impossibility results in a version of the auction problem where if there are like buyers and sellers and they're gonna like trade some items from each of them, like there is a impossibility result stating that any robust mechanism is always inefficient. So all these results like And like actually that there are like far more set of like impossibility results. For example, in matching theory, some financial markets, and some information design problems. So like there are too many like pessimistic results. One question here is that whether we could achieve a relaxed version of the objective functions rather than this exact optimality, which is actually like what many algorithm researchers are doing these days, okay? So, and there are also like some further limitations on like these classic results. For example, like typically most of the theoretical economists assume that they have some like distributional knowledge on the problem. I mean, for example, like valuation of bidders towards the item. That is actually like not always practical. And also, like typically, economists like analyzes certain outcome by analyzing certain equilibriums, not analyzing all the equilibriums. But like, for example, as a computer scientist, what we typically are interested in is that we are interested in the worst case performance of the algorithm, for example. We can ask some similar questions in this context as well. Okay, so like summing up these like questions, there are a lot of like algorithmic and computational questions that we can ask in these contexts. For example, first is that how we're gonna efficiently compute the outcome of a game. Like how we're gonna, whether we can efficiently compute the equilibrium. Is it possible? What if a relaxed version of that, approximate version of that? Second question is like in terms of the mechanism design problem, if we can like design some like approximately efficient mechanism, potentially in polynomial times, okay? Third question may be if we don't have like some certain prior information on the problem instances, like whether we can do that somehow in a robust manner, or whether we can design some learning mechanisms, like we collect some data interactively and use that to like design some efficient mechanisms. And the fourth question is about like outcomes under worst case equilibrium, which is often called as a price of anarchy. We're gonna, in this talk, I talk mostly about the first two questions because like these are like very standard like questions in algorithm game theory. So these four are actually the one of the four of the most like well motivated questions in algorithmic game theory that distinguish the classic game theory problems from this algorithmic game theory. Okay. Any question? Yeah.
Can you explain what relaxed objective is?
So for example, like, yeah, there is a like an impossibility theorem for a double auction problem, which I'm gonna probably define a little bit detailed really shortly. There is a result stating that if you design a mechanism so that no one is gonna lie about your true bid, then that such a mechanism cannot like achieve certain objective functions, cannot optimize the objective functions. Then our question, okay, the economists typically just solve that problem, prove that theorem statement, and it is done. But like, as a like algorithm designer, what we're interested in is that like what will be the approximation guarantees of those like problems, for example. Yeah, thanks for the question. So overall, like the theme of this like this research area is about like investigating game theoretical problems with modern algorithmic and computational lens and also optimization lens. Okay, so actually this is also highly related to the topics in theoretical computer science. What the theoretical computer scientists are doing is that, okay, like in like 30 years ago or even for now, many researchers are doing solving some offline optimization problems to solve some specific problems given full knowledge of the problem instance. However, there is also some emerging areas in modern computational models, such as what if we have some partial knowledge on the problem instances, or what if we have some resource constraints on the space, or very like some information, something like that. So there is some branches of algorithm design called as like online algorithm, streaming algorithm, sublinear algorithm, dynamic algorithm, something like that. And actually, algorithmic game theory and algorithmic mechanics design is very similar. Like it tries to, there's some uncertainty here because like the problem instance based by the algorithm designer is actually governed by strategic agent. It's not just fixed in an exogenous manner. Okay. There's also a constraint such that we want to design some algorithm that incentivizes the participants to do something that they desire, right? Okay. Yeah, so broadly speaking, algorithmic game theory and all these like line of researches are belonging to what is often called as econ CS, economics and computation, which is the intersection of like CS, econ, and operations research. So I will give a little bit of like logistical information about this research area, if you may have wondered. So there's one of the top, one of the most prominent conferences in this area, which is called as ACM Conference on Economics and Computation, ACM-EC, for example. It's very like prominent conference, and it also has very low acceptance ratio, and also like very famous researchers are coming to these conferences, and there are also like journal forwarding options so that the conference itself reviews the full paper, but it has an option to only submit an extended abstract. If you do that, you can also forward your full paper to some like prominent journals in IOR, including like Informs or MSMOR, and also like top journals in econ and theoretical computer science as well. And this is actually like run by it's called as ACM SIG Econ group. It also publishes some like monthly exchanges and announces some awards as well. Actually, I did some like I did some data analytics to see the statistics for this year ACM-EC conferences. It turns out that there are 45% of papers from computer scientists, also 25% from economists, and 30% from operations research and managed studies, showing that this is indeed a very interdisciplinary area. And also it's very prominent since like even 30% of the like submissions were from top 10 schools in USA. So like many researchers in this area, not only like publishes in these conferences, but also some other conferences as well. For example, if it has a little bit more of algorithmic flavor, then we often publish seminar papers to CALOP-POSTECH, which is some conferences, theoretical computer sciences. It has some like learning flavors, and we also submit to machine learning conferences as well. So there are actually some econ CS groups in universities in USA as well, and also like some research groups in Microsoft Research and Google. Okay, so this was about some like community information, and so this is actually a little bit the summary of the game theory, which I'm not going to talk about the details of all of this, but okay. So actually, the line above is about like game theory and equilibrium computation, equilibrium existential results. The below line here is rather about like the foundation of mechanism design. Okay. So the game theory actually dates back to 1944 by Nash. Actually, like there is some controversies that it actually dates back to a little bit older period of time, but actually Nash is the founder of game theory. And there were a lot of researchers trying to sort of like refine the notion of the solution concept and also prove a little bit more general theorems, for example. Also, on the other hand, the mechanism design problem based on the foundation of game theory dates back to 1951. Steinhaus develops a foundation of the fair division problem, and 1960 and 70 there was Mearson, Maskin, and Hurkis who develops the foundation of the mechanism design, which generally subsumes the auction design and contract design and some broader set of problems here. Okay? And 1980 and 90, there were a lot of like researchers studying these mechanism design problems from economist community. And there was a foundation of like principal agent problems by Holmstrom and Hart, and also a significant advance on auction design by Wilson and Pearson and Wilton. Notably, these people with blue color, they all received the Nobel Prizes in economics. And also, this is the history of the algorithmic game theory that sort of like complements this line of research here. Okay, so it has rather relatively short like history. So the first introduction of the algorithmic game theory dates back to 1994. Actually, this is not the introduction of the algorithmic game theory, but Christos Papadimitriou, he introduced a complexity class like MP, P space. He introduced a complexity class called as PPAD, which turns out to be exactly the complexity class that captures the complexity of computing a Nash equilibrium. Okay, and also this is what like this is about like okay, after he introduced the concept of the PPAD, like in a decade later, Daskalakis, Goldberg, and Papadimitriou shows that computing Nash equilibrium is PPAD complete for at least three number of players. Okay? And this is improved by Chen, Deng, and Tong, proven that it is also PPAD complete for 2 players. Okay? There is also algorithmic literature on mechanism design problems here. Nizan and Ronan, they actually wrote a book called the Algorithmic Game Theory, Algorithmic Mechanism Design, which was thought to be a foundation of algorithmic mechanism design. Actually, there is a like algorithmic game theory version of the scheduling problems that many of you may be familiar with. And also there's a foundation of algorithmic fair division problem, auction design problem. But I will only talk about a few of these problems today. Okay? So what I'm gonna talk about today is first it is about like auction design problems. And then I'm gonna very briefly talk about truthful scheduling, strategic version of the scheduling problem, because I'm not familiar with scheduling problems actually. And then I'm gonna talk briefly about fair division problem, and then complexity of computing an equilibrium. Finally, I will talk some of my researches on these line of contents. Okay, so first, auction design problems. So any questions so far? Okay, great. Auctions is actually one of the most like old markets, which dates back to even like ancient Greece. So it is a market or organization to allow exchange of items, physical items typically, but also digital items recently. So here we focus on a problem setup where we are a seller, we have an item, how we're gonna sell this item. So we have like buyers who have some potential valuation on the item. For example, I value this item, I value this water like $5, but as a seller, I don't know this valuation, the valuation of the buyers. So we're gonna design a rule so that the buyer is gonna truthfully report their bid, and also so that we can probably like maximize our objective functions, which could be varying. For example, like I want to maximize my revenue, or I also want to like just maximize the social welfare. I mean the welfare of the entire society. Formally speaking, let's consider a single item seller. A seller who has a single item and potential buyers, and buyer I has a valuation VI, which is drawn from a distribution DI. As a seller, we don't know the VI. So this is called as a private valuation setting. But we know the distribution DI. So this is actually called as a Bayesian mechanism design because we have some distributional knowledge here. Okay? So what we're going to do is to define mechanism X and P. X is an, So X is an allocation function, then maps the reported B's of the buyers to some allocation functions. So, for example, it could be, for example, like my auction format could be, if you guys like bid in this manner, I'm gonna always sell my item to this buyer. But it could be also the case that, okay, with probability 0.5, I'm gonna allocate the item to this buyer, but otherwise I'm gonna like randomly allocate the item. For example, this is also possible. Just a reason the allocation function could be a real value, not exactly an integer value. A payment function is generally a mapping that maps the reported B's to payment function for every buyers here. Okay. Okay. So what will be the buyer's payoff here? The buyer's payoff will be the true valuation. The buyer I's true valuation is VI here. Okay. And XI is the allocation probability that this buyer will be receiving the item, and minus the payment. Okay. Here you can just think of this like hat of VI as a reported bid of this buyer I, rather than the true valuation. Okay. There are some standard assumptions in the auction design literature to make the problem a little bit more simpler and analytically tractable. The first is that we assume that distributions of the buyers are independent. This is kind of like reasonable because like my valuation of this water perhaps does not depend on someone else's valuation. Also, we assume risk neutral buyers, meaning that they try to maximize expected payoff. This can be not very practical because like there may be some risk averse behavior of the agent. For example, if there is a large chance that I'm going to lose a lot, then probably I want to be a little bit more conservative. Okay? Actually, there are some literature trying to tackle these assumptions, especially the first independent assumptions. There are some like a large line of works trying to study what is called the interdependent scenario, where my valuation on this water perhaps depends on someone else's valuation as well. Okay. Okay, so this was the buyer's payoff function. And what is the seller's objective? So perhaps I'm interested in maximizing my own revenue because I'm a selfish seller. Also, I can, perhaps I'm a little bit more generous because I want to maximize the summation of the welfare of every participant here, which is the summation of VIXI. So the reason that this is called the social welfare is that because like whenever a buyer pays something to me, then my utility increases in that amount. This buyer's utility decreases in that amount. So that cancels out. So the only remaining social welfare is just about who gets the item with which probability. Okay. Okay. So like as I said, there are some as in the game theory problems, there are some solution concepts that is typically widely accepted in the literature. Okay, so we want what is called as truthful mechanism, meaning that we don't want the agent to lie about their valuation. Actually, there are some theoretical reasons that this is desirable, but let's discuss it later. First, like dominant strategy equilibrium is defined as an equilibrium. Okay, I think we already like discussed this one. So this is about like regardless of what others bid, actually, I'm gonna like just truthfully bid. So that is called as a dominant strategy equilibrium. And what is called as a dominant strategy incentive compatible mechanism or desync mechanism is such that reporting truthfully is dominant strategy equilibrium. So no one has an incentive to lie about their true valuation. Okay. Also, there is a very natural constraint such that their expected utility should be non-negative because otherwise they probably has no incentive to actually participate in the auction. Okay. So overall, we want a mechanism that is DC, individually rational, IR mechanism, while maximizing our objective function, social welfare or revenue. Okay, if you think about this problem setup a little bit more, then you may realize that, okay, this is actually a very restricted class of mechanisms, auctions. Because like, if you think about real auctions, there is an auction called as English auction, where there are a lot of multiple bidders here. They raise their hand, they submit their bid, and then they should always like increase the bid, and the final bidder who submits the final bid, meaning the item, pays that amount. Okay, that class of auctions are not actually captured by this definition, but that's fine. Why is that? There is a seminal result by Mearson proving that, okay, it is fine to focus on the class of mechanism that we have defined thus far. So the outcome of those other auctions will be exactly equivalent to this auction format. So there's only this auction of this format that has exactly the same outcome. And it is even the case that, for example, if we think about, okay, so we have defined a truthful auction here, but like there could be some auctions that, okay, so like they may not truthfully bid their valuation. They may lie very strategically, but it could be the case that the outcome for the seller may be better off in that like very complicated equilibrium. Okay, so probably truthfulness is not something that we always want to do, but this revelation principle. Sorry, there's a typo here. It should be principle. It also says that okay, if there is such an auction, then there is always equivalent. There is always an auction. A truthful auction with exactly the same outcome. So it is exactly safe to just focus on this class of mechanisms where the buyers just like directly submit their bids, and then it is fine for us to focus on truthful mechanisms. Okay. So this mechanism format is called as a direct truthful mechanism, actually. Here are some results in this auction design literature. Okay, in the single dimensional setting, so what is single dimensional? There is a single item and the independent valuation. So why is it called single dimensional is that there is only one real value required to represent the buyer's type. Here, the buyer's type is the valuation for the item. Okay? So if the seller wants to maximize the revenue, there is a mechanism called as a VCG mechanism, a Vickrey-Clark-Gross mechanism. And also, if the seller wants to maximize the revenue, on the other hand, there is a seminal result by Mearson at 1981, showing that using some techniques called as a virtual valuation and iron technique, the seller can actually maximize the revenue very easily. Okay, what if we turn to multidimensional setting, meaning that there are multiple items. There are for example, this water and ramp projector here. I have potentially some combinatorial valuations. For example, I value this $3, $5 for the projector, but together I value them $10. So valuation for the item towards set of items could be arbitrarily combinatorial. Even in this case, it is shown that if the seller tries to maximize the welfare, VCG mechanism is still optimal, meaning that this is the truthful mechanism that actually maximizes the welfare. But there is also a question that if this is efficiently computable. For the single dimensional case, it does yes, but for the multidimensional setting, it's actually not exactly always. I think, yeah. So the reason is that if you think about just everyone just reports their valuation truthfully. I mean their valuation function, combinatorial valuation function truthfully. And if you just think about the allocation problem to maximize our allocation of the items to the buyers so that we just maximize the valuation of the buyers allocate those items, that problem could be very hard. So if that problem is solvable in polynomial time, then it's shown that VCG mechanism is also optimal and can be computed efficiently. So So like for the multidimensional setting, welfare maximization problem, it is easy, rather relatively easy because VCG mechanism is still optimal. But what if we want to maximize the revenue? It turns out that this is a very hard problem. So like 10 years ago, there was a paper by Daskalakis, Ekelbaum, and Chamos showing that there is no expected polynomial time mechanism unless some widely believed complexity assumptions, for example, like P is not equal to NP, even for very simple instances. So like this means that like the revenue maximization problem, unlike from the welfare maximization, is very hard. Okay, and this is even true for a single additive valuation buyer. So meaning that if there is just a single buyer whose valuation is just additive over multiple items, if we have like multiple items, then this problem is very hard. So actually, like this problem, the revenue maximization turns out to be notoriously hard. It's not just like hard, but very hard. So for example, consider a single additive buyer. We have these two items, and we have like an additive buyer, just a single buyer who just like values two items separately. Okay? And the payoff function should be just like summation of each of the items. So what happens is that, okay, we know that the distributions are independent for this valuation. So is it fine to just price each item separately? Turns out to be the case that it is not. Yeah, it turns out it is not. Or it could be also questionable whether we could just like simply price the bundle of the items in a single shot manner. Turns out to be it is not optimal. Or either we can do either of them. We do either price them separately or either bundle them and just like price them together. It is also not optimal. Or like what if we do that simultaneously? Like post prices for each of the item and post the price for the bundle. Is also not optimal. So what is actually optimal? There is some residuals. Okay, actually like all these like residuals holds even for very simple distributions like uniform distributions over 1 and 2, 0 and 1, something like that. And what actually the seller needs to do here is to offer what is called as a lottery. So for example, like if you buy this item at $4, I'm gonna give you this item with probability 0.4. But if you buy this item at $6, I'm gonna give you this item with like probability 0.8. So this each of entry that represents the price for a set of items and the probability that you're gonna get that items. That's called as a menu. Each entry in the menu of our auctions, okay? And it is even true, it even turns out that like the optimal mechanism actually should offer infinitely many entries in the menu to actually maximize the revenue. So meaning that this is like very intractable problem, okay? Any questions? Okay, so what we can do given this pessimistic result here. So as I said, okay, like actually we probably don't need to like try to solve for the exactly optimal revenue maximizing like mechanism. Perhaps it is fine to just do something like 99% of the optimal. So the option one is to design approximately efficient mechanism. So there are some residuals for some versions of the combinatorial auctions here. For example, there is a known two approximate mechanism when the buyer's valuations are so modular, or what is called as XOS function. XOS function here is a class of combinatorial functions that is general than submodular, but stronger than subadditive. Okay. And also there's a log M approximation mechanism for subadditive functions. Actually, it is an open problem that whether this could be improved to constant or not. If you solve that, that will be a very seminal like result in the literature actually. So like these results are actually coming from very classic problems in theoretical computer science or optimization. What is often called as a profit inequality. I think we're going to deal with that later. Okay. So this is one option. What is the other option? So another option will be, okay, we have too many features that we should consider for our mechanism. But what if we dissolve some of the features? For example, what if we only pricing each item separately? Or what if we just like allow packaging the entire item or so? Then there are some results showing that there could be some efficiently computable mechanisms. But is it also like known? It is also not known that when like these features are necessary or sufficient to have some optimal mechanisms or approximately optimal mechanisms. Another option here will be, okay, so here like we disallow some features in a qualitative manner. We just like disallow bundling, disallow like pricing separately. But what if we just limit a little bit more quantitatively? For example, we have known that we should like offer our menu, including infinite number of entries to maximize the revenue. But what if the question here may be like, if we have like, for example, constant number of entries in the menu, then how many like to which approximation factor we can actually achieve? So there are like some papers in this direction as well, showing that okay, if we have like polynomial number of menus, polynomial of like, so actually like this number of entries here is called as a menu size complexity in the literature. So this menu size complexity, if that is polynomial, is shown that you could achieve some constant fraction of the optimal revenue, but it's not known that whether that could be like very arbitrarily or symptotically close to the optimal mechanism. It is known that if we allow exponential number of menus, we can like approximate the optimal mechanism very closely. Okay, any questions? One open problem here is actually, okay, there was a seminal result by Gonzalski, Babayov, and Nissan here, showing that some constant fixed fraction is possible for polynomial like number of menus, but that constant fraction is very low, like 0.001, something like that. So one big research question is whether we could like obtain some like approximation guarantee very close to 1, like 99% with polynomial number of menu size complexity. Okay. Okay, so okay, let's move on to another problem in AGT. So this is what is called as a game theory version of the scheduling problem. I think probably many of you are actually like very expert in scheduling problems, so probably is already familiar with this problem. My apologies that I'm not actually familiar with scheduling problems. But I will just give some like brief introduction to the problem. So we have m tasks and we have n unrelated machines. And each machine I needs like the time Tij to process test j. And what we're gonna do is we're gonna allocate each of the tasks to machines in an efficient manner to minimize the processing time of all the machine, which is often called as a make span of this scheduling problem. So this is called, please fix me if I'm wrong. So this is called as a make span minimization problem, which is the objective is to minimize the maximum processing time of all the machines. Okay. So what is a game theory version of this problem? So we can consider each machine is an agent. So probably you have a machine. You need to pay some bills to actually run the machine. You need to then it might be the case that, okay, I have some very high performance machine, but I don't want to use my one because I want to keep it very fresh, okay? So they may falsely report their processing time, okay? So like our question is that how we're gonna design a mechanism that determines a scheduling of the task to the machine, and also payment for each of the machines, so that each of the machine have like incentive to truthfully report the processing time. When their utility function is the payment function minus the processing time of the summation of the processing time of the task allocated to that machine. Okay? I think perhaps there is a version with another utility function, but actually I'm not familiar with them. So this is a standard problem setup in the strategic scheduling problem. Actually, this is proposed by Li Zhan and Ronan in 2001 in the book they wrote about like algorithmic game theory. What we want to do actually here is that we want to design a mechanism that is truthful as well as approximatmately efficient with respect to the optimal processing time in the non-stretched version. So there will be a solution in the non-stretched version where we have the private processing time. And then we want to like benchmark, like we want to approximate that benchmark. Okay? It is shown that there is actually easy over-band approximation algorithm via the application of the BCG mechanism. So one thing to note here is the BCG mechanism turns out to maximize the social welfare. On the other hand, in this problem, we have different objective functions. But okay, it may be fine because BCG mechanism has approximate vector that is linear on M, which is not great actually because it increases as the number of machines increase, but okay, still. They also showed that any truthful mechanism has approximation vector that should be worse than 2 approximations. I should remove omega here, but okay, any truthful mechanism's performance should be worse than 2 approximation. And they conjectured that no mechanism is essentially better than BCG mechanism. It's very like pessimistic and very bold conjecture actually, because like this means that like no mechanism could achieve something better than all-band approximation ratio. Actually, it turns out that through some like recent works here, the conjecture turns out to be true. Actually, I remember that one of these papers received the best paper award in this conference, but I don't exactly remember which one is that. But actually, okay. Anyhow, the result is that like this pessimistic and very bold conjecture is true, but it was only about any deterministic mechanism. So it has been not known that what is the approximation vector achievable for like truthful randomized mechanism. Or what if like we can have a better approximation ratio in some restricted regimes like identical machines or identical tasks or so. Okay, any questions? Yeah, we have remaining 2 problems. Okay. I think it is quite very algorithmic problems, which is very simple, but algorithmically very interesting. So as I said, the economics, especially the microeconomics, is all about study the behavior of individuals. I mean, human individuals, when like resources are scarce. So they are like it is not the case that all human beings are satisfied with what they have. We always envy someone else's. We always like complain about, I don't have this resource or source. Okay? So unlike the mechanism design problem was actually about like, what if these individuals are even strategic? But social choice problem is a little bit like easier version of the mechanism design problem is that, okay, if we truthfully know the preferences of each individual towards, for example, some resources, how we're going to efficiently and fairly divide those resources. So that is what is called as a social choice algorithm, a social choice problem in the microeconomics. And similarly, the researchers in algorithmic game theory community, they study a lot about like some algorithmic problems for these social choice problems. So actually, come to say that, okay, if we have some like allocation function for the social choice problem, then we can use that allocation function to implement as a mechanism. So that meaning that if we want to allocate this specific allocation function, but how we're gonna do that? We now have strategic agents, so we need to like elicit their like valuations truthfully, and then we're gonna base a mechanism design problem there. Okay. So let's first talk about a general problem statement of the fair division problem. There are n agents and a set of resources m here. Could be finite or infinite. We're gonna specify that later. And the valuation of the agent for the resources is gonna be, okay, this may be not mathematically very formal and well defined, but for now, let's assume that the resources is just finite for now. The valuation is combinatorial. It could be non-negative or it could be negative even, meaning that probably we're gonna divide chores, for example, like houseworks, okay? And then what you're gonna do is that like we're gonna partition the resources among the agents. There are some notions of fairness. So what is actually like fair algorithms? There are a lot of controversies on, okay, this notion is fair, this notion is more practical, but like these literature, there are some like seminal literature on economics, like stating that some, like axiomatizing or developing some foundation of why certain notions of fairness are like desirable. Okay. Okay. So first, let's talk about what is called as a cake cutting problem. So we have a cake. We're gonna divide the cake. We have a valuation for each part of the cake. Cake could be very heterogeneous, meaning that this piece of cake and this piece of cake may give me very like different valuation. I hate this piece, but I like this piece of cake. Okay, so the cake could be represented as an interval 0 and 1, and we assume some assumptions for the valuation functions, meaning that okay, if the agent gets all the cake, then the valuation is 1, meaning that valuation is normalized, and it is divisible, meaning that for any lambda in 0, 1, bi x comma z, there is some z in the interval x comma y, such that it is exactly the point that divides this cake into lambda portion of that. Okay? It's a very reasonable assumption. We also assume a very simple additive valuation for the cake. Okay, so if we have 2 pieces of cakes here, my utility is just sum over 2. Okay, so now let's dive deep into what is the desirable notions of fairness. So, for example, there is a widely accepted notion of fairness called as proportionality, meaning that on allocation AI are proportional if all of the agents' utility, valuation is at least like 1 over n. So this is not easy to like achieve. Not trivial to achieve this because valuation could be very like different for the agents. Okay, and there's also envy-freeness, meaning that I don't envy anyone else's allocation. My valuation for my allocation should be at least better than someone else's allocation. My valuation on someone else's allocation. That is about envy-freeness, so that there's no envy between the agents. There is also a notion called equitability, but let's skip that today. Okay, so if we want to solve this problem, actually, we should have some proper computational models here. So what is typically assumed in the literature is that, okay, there is an oracle. We have an oracle computational model that returns if we give input as x comma y here, then it gives us the valuation for that interval for specification. That's called as an evaluation oracle. It's also called as there is also a notion of like computational model called as a cut oracle, stating that if we give s comma alpha, then it gives us the point y such that the agent valuation is exactly alpha from x. Okay, so this is a side slide stating that this notion of ambiguity actually dates back to some protocols in ancient Greece, but let's skip that day. So let's get into details of the some seminal results in the fair division literature. So for proportionality, for two agents, I mean even for ambiguity, there is a very simple algorithm. So for example, suppose that we have like only like me and you want to divide the cake fairly, so that I don't envy you, you don't envy me, and our valuation for the cake is like at least 1/2. I think probably some of you may have guessed what the algorithm is. So what is called as cut and choose algorithm. This is meaning that it's very like widely used in the real world scenario. So it is an algorithm that I want you to cut the cake, but I will choose first. Then it is shown that this algorithm exactly outputs an allocation which is proportional as well as ambiguity. Actually, for proportionality, it turns out that there is an algorithm that exactly finds the exact proportional allocation in n log n time, which is a very strong result, actually. So the question here becomes more non-trivial for ambiguity. For n equals 2, okay, cut and choose. It only requires 2 queries for the entire protocol. For n equals 3, that is a result by Selfish and Conway, showing that it requires at most 14 queries to make the cake ambiguity. It is also shown that, okay, the query complexity for any number of n is finite, but they were not able to parameterize the upper bound there until recently. So there is a very like ridiculous result by Aziz in 2016 showing that like for any n agents, the recurrent queries is at most n to the 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 n. So probably no one cares about like this result in practice, but anyway, this was a big advance from theoretical perspective. Okay. Actually, it is known that it is necessary to invoke n-squared queries for any number of agents. So there is like very large gap in this upper bound and lower bound. I think if you like resolve any of this gap here, then probably you'll be able to receive a lot of like media attention. Probably. Okay. Any questions? Okay, great. Yeah.
Is there any literature like about the cake design problem?
Oh, cake design problem.
Reverse cake honey.
Oh, that's a very good question. Yeah. I'm not interested in cake designing, but I mean, I'm not a fan of cake, but but I think. Okay. I haven't heard about anything, but probably it could like induce some very good research questions. So yeah, thanks for a very good question. Okay, any other questions? Great. So okay, so far we talked about cake, which is in this like fractionally divisible. But what if we focus on some physical items like this water that is not divisible? then the problem becomes like very, very much more challenging. So we have M good, and okay, so for now we're going to focus on good, meaning that the valuation is always non-negative. Okay, we have M goods, a valuation function for each agent which is combinatorial, which is potentially combinatorial. Okay, it is very trivial to show that ambiguous is not possible. If you just consider one item, three agents, if you just like, regardless of what agent we give the item to, the resulting allocation is always not ambiguous. So computer scientists try to relax this notion of ambiguous. What is the most like straightforward direction to do that? They introduce the notion of ambiguous up to one good, EF1, showing that okay, my valuation of my allocation should be at least better than, sorry, this should be capital A here, should be at least your allocation except some item, one item from your allocation. So if we appropriately exclude one item from another agent's allocation, then my allocation should be better from my perspective. That is what is called as a ambiguous up to one good, EF1 allocation. You can think of a very simple algorithm, what is called as a round robin algorithm. You just like let each agent arrives, pick each item sequentially, and repeat that process. That allocation turns out to be ambiguous up to one good, actually. There is a little bit more stronger notion of the ambiguous here. Ambiguous up to any good, meaning that the G could be arbitrary, should be arbitrary. So even if we exclude worst item for you, I mean worst case item for me, I mean that should be at least better for me. Okay, so this is actually a stronger notion of the ambiguous. Ambiguous up to any good. This is called as EFX allocation. And it is shown that this exists for identical valuations. Well, all the agents have the same valuation function, but I mean, this is only proven like 6 years ago. And it is also proven that it exists for like two agents with additive valuations, like 6 years ago. And 5 years ago, it is proven that it exists for three agents. Yeah, it also received some best student paper at EC 2020, but I mean, this is just for three agents. There is no known progress, I mean, not any progress known for any number of agents here. This is a very big problem in this community. Actually, the algorithm, this is about just existence. So if the algorithm needs not be polynomial time. So if you just like provide something using some like probabilistic like argument, that should be fine. Okay. So any questions thus far? Okay, great. So as I said, so these were just like some set of the problems widely studied in this literature. There are a lot of like other problems like double auction, voting theory, matching theory, prediction markets, all of which I think are very interesting. So you might want to check them out. So before like presenting some grasp of my research, I think like I spent too much time on these other problems, but let me briefly go over some results on the complexity of computing in equilibrium, and then very simply about my research. I will just keep these like notions. So there is a computational complexity introduced by Papageometriou, 1994. It's called as a polynomial parity argument on directed graphs. So suppose that we have a graph where each of the vertex only has one, at most one predecessor and at most one successor. Okay? Then it is known that there is a like lemma called as a parity lemma, showing that if there is a vertex with no successor, then there's always so this is actually called as a source. Then if there is a source, then there is always this sink, meaning that there is no successor. There's always a node with successor, and at least there's one such vertex. Okay. Then the question is that, okay, if we are given that there is at least one sink of that, and if you're given the sink of that graph, how efficiently could you compute? Could you find the sink of that graph? So that is called as a polynomial parity PPAD. I mean, this. So there's a name of this problem, but this actually is belonging to the complexity class called as a PPAD, actually. Okay. So it turns out that the problem of finding the Nash equilibrium is exactly it has exactly the same computational complexity with this problem. Okay, which is quite surprising. I was planning to provide some connections between fixed point theorem and Nash equilibrium and some other problems, but okay, I think this is not very important. Okay, so in any way, so PPAD, unlike the problems in P and MP, P and MP, those problems are decision problems. So whether we can output yes or no in polynomial time or not. PPAD problem is a little bit different. We need to find the sink of the graph given a source. This is a search problem rather than a decision problem. So we need, this complexity class that involves this PPAD is a little bit different than P and MP. So P and MP, there are some complexity classes, P and P space XP, something like that. But there is another version of another branch of the complexity class for search problems. But you can easily found, you can easily show that if we know that there is always a solution for this problem. For this graph problem, we know that there's always a sink of the graph, and our task is to find the sink. Intuitively speaking, this is easier than to find the sink when we don't know that whether there is a sink or not. So it is known that this is actually easier than NP, but it is not. It is not shown. It is not there is no evidence whether this is strictly harder than P or not. So that is actually very big open problems in computational complexity. And also still most of the researchers believe that this is not belonging to P. But still because finding Nash equilibrium was quite hard. It is there is no polynomial time algorithm developed for these problems, and it is largely believed to be hard. And then the question will be whether we could derive approximate equilibrium in an efficient manner. It's also a big research problems, and also whether we could design a learning algorithm where the players do not know the payoff functions of all the players, but they just run some learning algorithm over time, and then whether all the systems could converge to some equilibriums. It is known that there is an algorithm which is called as a no-regret algorithm, which is actually inspired from the online learning literature, such that graduating dynamics of the system converges to what is called as correlated equilibrium. It's actually a little bit relaxed notion of the equilibrium. It subsumes the Nash equilibrium, but it is not known that whether there is an algorithm converges to Nash equilibrium or not. Learning algorithm. Okay, so I think I have 10 minutes for my research. So I will just talk very briefly about it. So my research is about studying some line of research in this context, but the one major theme of my research is that like to design an efficient delegation mechanism. So like in this era of like ChatGPT and Gemini, we delegate many parts of our daily lives to like agent, expert, and like, for example, students, colleagues, team members. Even when I prepare like these slides, I consult ChatGPT a lot. Okay, so then the question here is that the agent may be, so for example, like let's think about we delegate some tasks to an agent. For example, I delegate this presentation to like my brother, for example. Then what could happen there? Like the agent may be strategic, so that the agent has like another pair function, ulterior motives in the decision-making process, so that it does not like behave in favor of myself. Okay. It could also be the case that the agent is misaligned. Still is like ulterior motives. Or it could be the case that like it has incomplete information about my preferences actually. For example, if you think about the LLMs, it is very good, but it sometimes outputs something that's very ridiculous that I don't actually want it to be output. Okay. So like my research question here is that like how we're gonna design an efficient delegation mechanism regarding the strategic behavior of the agent when their like pair functions are misaligned or there is some information asymmetries. Okay, I've been studying these like delegation process in like 4 representative scenarios. The first is that like if you think about like YouTube, this is all about delegation because like YouTube does not create content by itself. So it delegates the role of the production to content creators. How do they do that? They provide some proper incentives. Okay, so how should like these content platforms or like recommendation algorithm should design like payment functions and also recommendation algorithms to like incentivize content producers? Like one interesting feature here is that like recommendation algorithm decides which contents gets visibility, but this visibility translates to revenue directly because if my content is shown more frequently, then I get more revenue. And I also study what is called as a delegation of choice problem. For example, like let's suppose there is a CEO of a company who wants to maximize the revenue of the company, but there are some potential projects that we can focus on the next season. But the CEO has no expertise on that, so it delegates the decision of the choice between like these projects to CTO. Perhaps the CTO is rather interested in like committing to a project that is like technically involved rather than that has like potential like maximum revenue. So so this is one of the instantiation of the delegation that I've been trying to solve. This has a lot of like applications in organizations and markets. And also like in the auction problems, we were always like, typically it is always the case that we are just a seller. So we just sell the item. We have full control on like how we're gonna design the mechanism. But in like real world scenario, for example, like if you think about like the government tries to sell some goods, like demerit goods, like cigarettes, tobacco, alcohols, they delegate the role of the governance of the trade to some brokers. Some third parties. Okay? But like those brokers could be like strategic as well to make some arbitrages in selling at higher prices and buying from lower prices. Okay. So then my question here is that like if there is such a broker, what happens to the overall outcome of the auction, and what could we do in order to intervene in such mechanism? Okay. And also finally, this may be a little bit more trendy topic. We are delegating a lot of like information acquisition process to LLMs. here, like the question here is a little bit different. So the challenge here is that, okay, the LLM may not be a strategy because like this is my LLM. Like, I signed up for the ChatGPT at $200, but like this should not be strategy. But there's still a problem, so that the LLM is trained on like preferences of like a lot of like human. So those like human probably have like very heterogeneous like preferences on generating the output. So the question here is that how we could like align the output of the large language model or like generally just an artificial intelligence agent so that it provides something that is well aligned with my output. So the question here is not about like strategic behavior of the large language model, but it's rather about what if the large language model has like relatively restricted information about myself, then how we're gonna define some self-reinforcement, like reinforcing procedure to actually improve the outcome of the generative AI to align with my preferences. Okay. So the overall research goal is to design efficient delegation mechanism in these like applications. And if you need to do the delegation necessarily, then what will be the fundamental laws from the scenario that we can just solve the task by ourselves without delegation? If that is like very large, then probably we don't need to do. We should not do the delegation. Okay. So I've been like studying this problem, as I said, in these four representative domains. I was actually hoping to talk a little bit more about the delegation of choice problems because it has some like optimization and algorithmic feature, but I think probably I don't have like much of the time. So I will just stop here and I can move on to questions and answers. Okay. Thanks for listening and yeah, thanks for listening.
Okay, yeah, if you have some further question after the session, you can ask him. Yeah, thank him again.